Okay, let's start up again. So what we had left off with is Bob's failed his drug test. So Bob must be a drug user, right? End of story. So hand is Bob a liar? Okay, oops, my animation's a little screwed up here, but we'll work through it. So remember, Bob tested positive but swears he does not use opioids. So we're going to start off with our standard population, 100,000, and we calculate the base rate, so 1%, so it's 1,000. That means 99% do not use opioids. Don't forget that. And so this is where our sensitivity comes in. So 998 who are users are expected to test positive, but 2% are not going to detect positive. Of those who are non-users, okay, this test is 96% specific, so it'll correctly identify, the majority of people, 95,000 plus, as non-users. But look at that number. Almost 4,000 are going to have what's called, well, let's start from here. So these are called the true positives. These are the true negatives. So the test's correct and correct in two cases. Those two we missed are called false negatives. And then this, what I started to say here, those are called the false positives. So now you see that we're reframing our question, is Bob a liar, by saying, is he a true positive or a false positive? Right? So I think you can see where I'm heading for this. Look at the true positives compared to the false positives. Far more false positives than true positives. So we can come up with a statistic to get a sense of the value of this test by counting out all of the true positives divided by the total number of positives, and we say that the predictive value of this is only 20%. So that's the chance that Bob's positive is it's just 20%. So are you still willing to call him a liar? 80% we're saying? Those are more likely to be false positives. So the key thing here is the base rate. So if the base rate is rare, then the tests, no matter how good they are going to find far more false positives than true positives. Okay, so formalizing this then for any test, right? And you should start thinking immediately about, even for, base rate calling and sequencing when you're saying it's an A as opposed to a G. Okay, the chemistry, the machinery, and whatnot is not going to do that 100% accurate all the time. But we can consider the truth. Does the person actually use the drug, or in that sequence from that biological sample, is it really an A at that location? Well, there's two possibilities, right? Either a yes or a no. So the yes, that's the sensitivity of the test, and we'll call that A. If we test positive, okay, that's a true positive. The other possibility is if you test negative, but the person really does have the condition, does use the drug, okay, it was an A, but we called it something else, okay, that's called a false negative, and we'll give that C. So the other possibilities in the population, in truth, in reality, the person does not use drug. The base is not A, it's actually something else, all right? So if we test positive for the drug, this is a false positive, and we'll give that B. The other final opportunity here is this is a true negative, right? No and negative. Okay, so we can describe this in a variety of ways. A common way to do this is to describe the odds ratio. And the odds ratio is independent of the base rate. So this is the formula for it, but basically it's the idea is the ratio of the probability of an event, say test positive, relative to that event not happening. Okay, so that's A divided by B, C divided by D, or if you do a little rearranging, right, so it's A times D and B times C, so it gets to be a large number. So if there's nothing going on, the odds ratio is going to be about 1. So what this is, it says that this test is really, really good at what it does, that it detects positive readings, and more likely the positives are, that's our best guess as the truth. Okay? So we're going to introduce the likelihood then. It's a way of quantifying the evidence for a match. So the likelihood ratio, it's the ratio of two alternative hypotheses or scenarios. So for example, in your book, to define it as the prosecutor's view versus the defense's view. If we were to put this in the point of view of our example for Bob, so HP would be yes, he uses drugs, and HD would be no, he does not use drugs. Okay, and as your book interestingly points out, it's like the probability for the prosecution, they wouldn't be prosecuting an innocent person, goes the idea, so you set that at 1. I think a civil libertarian might have a little issue with that, but that's the way your book's introducing it, and so it's a good place to begin, right? So I'm not going to go through the formula except for to say what's cool about this approach is that you take the base rate, the likelihood that somebody has the condition or that they are a drug user is the base rate, and then you multiply it by the likelihood ratio that you calculate, and that then informs if the probability increases or decreases in terms of evidence in favor of does he use drugs, is he guilty of the crime. Okay, so here's my Bob, is he a liar work, and so you get two log likelihoods, sensitivity 1 minus specificity, and then the log ratio, likelihood ratio negative, so that's the defense point of view. That's how you would calculate it. And so anyway, we get 25 and 2 in 10,000, so pretty small. That's in the that's he's not a drug user. That's the likelihood that he is a drug user. And so when you take the ratio of those two, it's a huge number. So again, we would say that we have evidence that he is in fact a drug user. And then here's the details. The post-test probability is now we're pretty much 99.9% certain that he's a drug user. Okay. So why the different conclusion? Well, as pointed out, the one statistic suggests Bob's telling the truth. The likelihood ratio suggests it's unlikely Bob's telling the truth. Part of the answer is that the two formulations handle the base rate differently. In the base rate and the logarithm, the likelihood ratio cancels out. All right. The other part about this, though, is this is where it really gets tricky in interpreting probabilities. So you can do your calculations, and in both cases the calculations are correct, but we have to now make a judgment about which one is informing us about reality, right? And so this is I'm going to give an analogy here, and so it's called the prosecutor's fallacy. It's the idea that okay, the physical evidence at the crime scene matches the defendant, right? So prosecutor's fallacy would use probability something along these lines. A random person has 1 in 1 billion chance of having the DNA profile found at the crime scene. Therefore, the defendant who has this profile has 1 in 1 billion chance of being innocent. So the defendant is guilty, right? And the problem is that we're asking the wrong question. We're asking, what is the probability the evidence would occur if the defendant was innocent? And the correct interpretation is, given the evidence, what is the probability the defendant is innocent? It's a subtle difference, but it's an important one. Okay, so I'm wrapping this up here. It's straightforward enough to learn how to apply the equations, right? We showed you how to calculate allele frequencies, showed you how to calculate the mean. We even showed you how to run through the likelihood ratio calculations that you could use to do the match probabilities, okay? But the trick part about it is knowing the assumptions that go into those calculations. So I'm not going to get into this, but obviously, your book's pulling frequencies for different races, right? So you should appreciate in the United States, we've got a race definition problem. Part of it is, and I don't know how else you would do it, but you ask people, what race do you belong? But like in the census, we only count 5 race types, and then we have a grab-all bag that says other. Now, recently, we allow people to choose from more than one category. But obviously, there's a big difference between Asian, right? Who's Asian, who's African, et cetera, et cetera. Those describe, many, many different peoples. All right. And the other part is that the self-reported part doesn't necessarily correspond perfectly to actual genetics, right? So race is used as a shorthand for genetics, but it's not the same thing. And of course, from a statistical point of view, real populations are not infinite. And yet the assumptions about doing those calculations and coming up with those match probabilities as if they are infinitely large. Okay? So the question then is, given some of these other conceptions, what about the match probability? How is it affected? So I'm going to take you through a couple of little exercises. So we'll start you off with something simple. So how many ancestors do you have? Okay, well, you have a biological mom and biological dad, so that's 2, and then G could be generation numbers. So if I want to go back 40 generations, how many ancestors do I have? And so I sort of set up my table here. So 2 raised to the 1, that, okay, I was born in the 1960s, and so I have my 2 parents, okay, and then we can go back another generation, and of course this number gets larger and larger and larger. And going back into the 1300s, we're talking about having, what is that, 16, almost 17 million ancestors. That seems kind of interesting, right? But let's just put it this way. If I go back just 40 generations, so this is only 1, 2, 3, 4, 5, 6, 7. This is only, in the 20s. By going back just 40 generations with this simple formula, I'd have more than 1 trillion ancestors. So you should immediately go, that's impossible. Okay? In the history of the world, there hasn't been 1 trillion people. The world population back in 1000 AD was about 400 million, for example. All right? So what happened? How did this thing blow up to be something completely unrealistic? Well, the assumption is an infinite population model, and that's clearly not right. Okay? So real populations are not random, and so I have, this is sort of a reminder. So if this is the first generation, if I want to know the relationship between an allele in the 6th generation going back here, I just simply have to, from parent to offspring, half the genes are exchanged, right? So the formula for identity by descent is 1/2 raised to the n, where n is the number of generations. And so the relationship between this person here, right there, and this person here is about 1.5%. Okay? But what happened? How did I get 1 trillion ancestors? It's impossible. So you have to recognize that a phenomenon called pedigree collapse happens frequently in populations. And what that amounts to is, so let's go back to our first generation here. And so we have not just one kid, but there's 3 kids as part of the family, right? So this child becomes that adult and has a child. This child becomes the next adult, has a child, and so on and so forth, right? But the other child grows up to be this person, has a child with this person. This child becomes that person. That child becomes that person. That child becomes this person who marries or has children with this person, and so this person becomes this person. And so if you look at the relationship between A and B, it's no longer a half, it's actually now greater than a half, because we can connect the parents back through. And so this person would be an example of the focal point of the pedigree collapse, where an individual shows up in the pedigree more than once. Okay, so notice this isn't incest. This isn't anything like that. This is just populations get large and you tend to lose track of your relatives. I've always got confused by cousins second and third and fourth removed, but it's by the number of generations. So they're cousins, right? So they're removed by 1, 2, 3 generations. And then we come back together in the pedigree. So you'll notice in your book, just sort of a throwaway saying we'll use a correction for these kinds of realistic population collapses, if you will, called theta. And theta is actually a very small number, but that tiny little correction gives us a little bit better precision with our probability calculations. Okay. All right, so I'm going to go ahead and stop there. Look, there's a whole much more to do, and so I'm going to go ahead and use this to sell. I have a special topics class that I'm offering in the spring. Anybody can take it. It's Biology 480. It's the first one. There's another one. There's a cancer one. So this is genetic genealogy and ancestry. So we'll talk a little genetics, we'll talk a little bit of population genetics in particular, and we'll talk about using software to do some really interesting things. And for my forensic friends out there, that'll include, hey, can we figure out a suspect using publicly available genealogy databases? So thanks for your attention and hope to see you soon.